Hello everyone, day 2 of exponential functions 6.4. Let's get at it. Okay, we left off on some on your owns, and what I'd like you to do is I've kind of prepped these already, so these won't take long. There's some graphing involved here. Okay, so graphing exponential functions. And I'm just going to basically show you the graphs, and we're going to talk about them and see how we come up with them, all right? First one is y is equal to 3 raised to the x. Okay, so you see this graph here, y is equal to 3 raised to the x. And I want to focus on a couple things. Focus on where the origin is, when x is 0, okay? If 3 raised to the 0 power would be 1. So you see kind of where that's located. And then as x increases, function y just takes off, okay? So 3 raised to the 1 is 3 to the first is 3. 3 to the second is 9, and it goes off the screen here. But as you go towards on the negative side of x, -1, -2, -3, and so forth, you can see that y is equal to, let's just take a couple of them, 3 raised to the -1, okay? If 3 is raised to the -1, see that right here. Just change my screen here. Okay, there you go. You can see that that's equal to 1/3, all right? So 1/3 is when x is -1, okay? And as you go further negative, -2, -3, that value of y gets smaller and smaller and smaller. So the domain are all real numbers, and we're only going to have positive value of y, okay? So domain is all real numbers and only positive value of y. Let's take a look at another one, number 6. Y is equal to 1/2 raised to the x, okay? 1/2 raised to the x. So on this function, what we have is a fraction, 1/2, and we're going to raise it to the x power. So you can see where an x is 0, we're always going to be at that 1 point. So this value here is 1. There's nothing in front of here, it's 1, all right? So this is 1 times 1/2 times x raised to the x power. So when x is 0, y is 1, okay? Now, as you go to the right here, and as you get a positive value of x, we have ourselves x1, which would be 1/2, x2, okay, let's do that once. x2 would be 1/2 raised to the second, and that's equal to 1/4. Okay, because you have 2 raised to the second. 2 raised to the second is 4. And as you can see, as x gets larger here, your y is going to be positive, but it gets very small. Okay, so 1/4, then you'd have 1/8, and so forth. It gets extremely, extremely small. It doesn't go across the x-axis, but it does get smaller as you go further off in a positive direction with the x. Now, in the other fashion, if you have your negative x's here, -1, -2, -3, you can see it just kind of works in the opposite way, because when you put the negative in, okay, for x, let's just take -2. Okay, so you've got 1 to the -2 and 2 to the -2. What ends up doing is you end up kind of flipping this around. So this would be 2 squared over 1 squared, and that's equal to 4. Okay, so when x is -2, we're up here at 4. All right? So what happens is, as the x to the negative gets bigger and bigger, the y gets really large really fast. Okay, so you can kind of see how that works. Let's look at one more before we go on to our last one, number 8. This is number 7 on your own. Y is equal to -2 times 1/4 raised to the x. Okay, so let's just kind of talk about this one. So as x gets larger, you can see that y is negative, and it's always going to be, it's going to get really small. So if you have x is 1, you have -1/2. You can see this part right here. When x is 2, you have yourselves a very small number here, and as it gets smaller as you go that way. Okay. Now it crosses the y-axis at -2. Crosses the y-axis at -2. All right, so the y-axis at -2, and as you can see, this -2 is significant. If you remember back with geometric sequences, that was the 0 term. So when x is 0, this -2 is where it crosses that y-axis. Number 8. We're going to graph, in this case, y is equal to 1/2 x minus 2, describe the domain and range. Okay, so this is an example here of 2 graphs, exponential graphs, just the regular 1/2 x. Okay, we just covered that one. And then 1/2 x minus 2. Okay, so this is called a translation. We've covered this before, and it's going to be -2, so it kind of slides down the y-axis 2 units. So for exponential functions of the form y is equal to a times b to the x, the y values change by a factor of b as x increases by 1. Also notice that a is the y-intercept. Okay, so we've kind of had this before with geometric sequences when we were preparing for the MCA test. Okay, so this is going to be where the y-intercept is, this 2. Okay, 2 times 5 raised to x for this example here. So as x is increasing by 1, we're going from 2 to 10, we're multiplying by 5. 10 to 50, we're multiplying by 5. 50 to 250, we're multiplying by 5. And 250 to 1250, we're multiplying by 5. So our factor there is that 5. So this 5 is in this position, and that's raised to the x. And so our baseline is y is equal to a times b to the x. Okay, I have the exponential function. We covered that yesterday. Okay, one last thing today, and then I'm going to let you go, is example 5. This is an example of real-life application with exponential functions. So the graph here represents a bacteria population y after x days. Write an exponential function that represents the population. Okay, so you see this here. We have day 0. We're at 3. Okay, day 0, we're at 3. Day 1, we're at 12. Day 2, we're at 48. Day 3, we are at 192. And the 4th day, bacteria jumps to 768. 768. Okay, so this is we're going up 1 each time on the x side. So this is your x, and here's your y. So this 3 right here, whoops. So this 3 right here is where it crosses the y axis. Okay, it doesn't look like it's at 3, but it is. Okay, it's just above the 0 here where my cursor is. Okay, so that's going to be, so here's our exponential function. Y is equal to a times b to the x. Okay, so we're going to look for a, and we're going to look for b. Okay, a is going to be the 0 term. Talked about that in geometric sequence, or where it crosses the y-intercept. In this case, it's going to be 3. Okay, so our equation's 3. Then we're looking for this b. All right. So b is the factor. So what's the factor from 3 to 12? we're going to multiply by 4 to get from 3 to 12. So this is times 4, times 4, times 4, and times 4. So what that becomes is the b is the 4. So the exponential function 3 times the 4 raised to the x is the function that represents this population. Okay, so you got to find where that crosses the y-axis. In this case, it's noted right there, 3. And then we're looking for that factor each time. So go to get from 3 to 12, multiply by 4. 12 to 48, multiply by 4. 48 to 192, multiply by 4, and so forth. All right, now we're going to take that 3 times 4 raised to the x, and we're going to find the population after 12 hours and then after 5 days. Okay, 12 hours is 1/2 of a day. Okay, this is all in days. So we're going to go y is equal to 3 times 4 raised to the 1/2. Okay, 3 times 4 raised to the 1/2. And what that means is, because we have the 1/2 a day, and 4 raised to the 1/2 power, we're looking for the square root of 4 then, because this is the bottom number is the square root. Remember, we kind of turn that on its side. 2 is the square root of 4, so that would be 3 times 2, which is 6. Then we're going to compare that to after 5 days. Okay, over here we have 5 days. So we're going to take y is equal to, so this would be 6, and that would be for a 12-hour period. Okay, so so now we're going to look at 5 days. Okay, so y is equal to 3 times the 4, the factor, raised to the 5th power. 3 times the 4 raised to the 5th power. And that's equal to 3,072. Exponential function. So there are 6 bacteria after 12 hours. Okay, 12 hours is a 1/2 a day. Okay, that's why the 1/2. And then 3,072 bacteria after 5 days. And finally today, we'll do one more on your own. A bacteria population y after x days can be represented by an exponential function whose graph passes through 0, 100, and 1, 200. So here's our graph, 0, not our graph, but our table. 0, 100, and 1, 200. Okay, so what did you do to get from 100 to 200? You multiply it by 2. So there's your factor. So 2 is the factor. 100 is the y-intercept. So there's the function representing the population. Find the population after 6 days. Does this bacteria population grow? And it's the answer there after 6 days would be y is equal to 100 times 2 raised to the 6th. Does this bacteria population grow faster? No. This population doubles every day, but the population example 5 quadruples every day. Your answer there would be 6,400. All right, so that concludes the lesson for 6.4, exponential functions. Hope you found this a little bit easier to understand the second day. And hope you have a great day. Miss y'all. Take care. Bye-bye now.